Okay, so this is the next question. For each positive integer n, let xn be a real number. In the open interval 0,1/n, then which of the following statements must be true? Limit n tends to infinity, x n is equal to 0. Statement 1. Statement 2, if f is a continuous real valued function defined on 0,1, then f of xn, n is equal to 1 to infinity, is a Cauchy sequence. Number 3, if G is uniformly continuous real valued function defined on 0,1, then limit n tends to infinity, g of xn xs. Okay, so go through this question, work it out. When we come back, let's see the solution. Okay, I hope you all got the solution, so let's check it out. Statement number 1. Now we are given that xn is present in 0,1/n. That means xn is between 0 and 1/n. Now we are also asked or ascertained that limit n tending to infinity of xn is equal to 0. So we have to confirm whether it is true or false. Now from 1, as n tends to infinity, 1/n is going to be tending to 0. So this means since xn is less than 1/n, by squeeze theorem, this xn will be tending to 0. So this means limit n tending to infinity of xn is equal to 0. This in turn means statement 1 is true. Okay. Now let me go to statement number 2. So what is 2 stating? If f is continuous, okay, defined on 0,1, then f of xn, n is equal to 1 to infinity, is Cauchy. So is this statement true or false? Okay, so to have a confirmed outcome for this, let us revisit what we have done so far. Now we are stated here as xn element of 0,1/n. That's the first thing we've been given. Now as n tending to infinity, 1/n tends to 0. And by squeeze theorem, we ascertain that xn tends to 0. So this in turn means xn is a convergent sequence. Now in R, because this is our field, real numbers, convergence guarantees Cauchy sequence. Okay, Cauchy sequence. So this means xn is a Cauchy sequence. Okay. See, so far these are the deductions that we have achieved. Now the question states here that f is continuous on 0, 1. Okay, and it wants us to ascertain that f of xn is convergence. Now you have to understand this. Continuity of f will only apply at points where f is defined. This is a very crucial observation. Okay. Now clearly we are only given f is continuous on 0, 1. Clearly f is not defined, I would say, at 0. However, we know xn tends to 0. So this leaves us that we cannot apply continuity near 0. Why? Because f of xn can behave badly at 0. It can oscillate or even blow up. Okay. Now, does that mean we can outrightly conclude that f of xn, n is equal to 1 to infinity, is not Cauchy? Can we conclude that? No, we cannot. Right? Because we do not have sufficient information. So what we can say, we can only ascertain that we cannot guarantee that f of xn, n is equal to 1 to infinity, is Cauchy. Okay. Now just go and see what they are giving in the statement. Then, this is actually then, f of xn is a Cauchy sequence. Okay, so this is an outright confirmation. But we do not agree with this statement 2. Statement 1 is yes, statement 2 no. Okay, so that should be the actual choice for that. Now let me go to statement number 3. If g is uniformly continuous, real valued function defined on 0, 1, then limit entering infinity of g of xn exists. So this one will be our next attention. Okay, so this is the third statement. We are given that g is uniformly continuous, okay, on 0, 1. Now the key is uniformly. Okay, now clearly we know that xn is approaching 0, tending to 0, and xn is convergent. Okay, now with xn containing and being an element of 0, 1, g of xn must converge. Okay. Why? Because uniformly continuous is stronger than continuous. Okay, this is the key. So even if 0 is not included in 0, 1, uniformly continuous function will control the behavior of the function near the boundary. Okay, so this in turn means the limit n tending to infinity g of xn xs. Okay, that is the all important conclusion. In fact, this is actually forms part of a theorem for uniform continuous. Okay, so having mentioned the result to you, only 1 and 3 are our correct choices for this question.